Someone's fucking calling me. Hold on. Hello, welcome to Security, Cryptography, whatever. I am Deirdre. We are here with David. How are you doing, David?
I'm doing pretty good.
I liked your talk yesterday. If anyone didn't see David's talk, were you at Michigan or were you at Berkeley?
I wasn't anywhere. I was in my house doing a video call lecture for Zakir's course, which I don't know the number of, but that's roughly, here's how the internet actually works at Stanford.
Okay.
But all of my slides were branded as Michigan because...
That's why I was confused.
Because many of them were adapted from my PhD defense that I did for Michigan a few years ago. So despite currently wearing a Michigan shirt while we're recording this, and despite the block M's all over the slides, actually had nothing to do with the University of Michigan.
That's why I was confused. I was like, is Zakir at Michigan? No, he's not at Michigan. But anyway, we also have Thomas. How are you doing, Thomas?
I live.
Okay, good. Very good. And today, our special guest is Jason Donenfeld, creator of WireGuard. Hi, Jason.
Hey, happy to be here.
Good. Awesome. For those that don't know, WireGuard is the VPN everyone should be using nowadays if they have a choice on using a VPN. And not VPN as a service, but VPN as a protocol, as to be contrasted with things like IPsec. For cryptography nerds and for nice protocol aficionados who appreciate a nice, simple protocol design, WireGuard is a breath of fresh air compared to things like IPsec. So we're big fans of WireGuard here, and it emerged from the ether into the world via Jason's brain. So we are very excited to have Jason on our podcast. Can someone else fangirl besides me right now?
I can. I think, and Jason, I'm going to wait for you to shoot me down on this, but I think that WireGuard might be one of the more important things ever to happen to internet security. Not because VPN protocols by themselves are that critically important, although they are very important, but because the process that brought WireGuard, kind of into the market was so different than the process that brought other VPN protocols before it. In particular, IPsec, right? So there's a number of differences between, WireGuard and previous VPN protocols, but a huge difference between IPsec and WireGuard is that WireGuard is kind of one person's design, kind of free from standards committee, interference. You got to learn from what happened with previous protocols and come up with something that's kind of pure and not compromised. I have a very low opinion of internet standards cryptography and internet standards, kind of security protocols in general. And I think WireGuard's one of the first times in my career I've seen, something get this much adoption without having to, get through the filter of, the IETF. Am I crazy to think that?
I mean, I'm flattered you think it's so important. I mean, I guess time will tell there, but certainly the process that's brought it about is very atypical in that WireGuard came about just me putting it out, and it's been successful. I mean, a lot of people have made different pieces of VPN software themselves and put it out there, but it doesn't gain adoption. It's the crazy thing about WireGuard is it actually worked, which I didn't really even intend to do when I began. I just wanted the thing to exist because I needed it.
And what did you need it for specifically? Because I love this origin story.
Yeah, I guess a couple things. The initial impetus is I moved to France in 2012, and I wanted to be able to use U.S. internet, and I was familiar with OpenVPN and IPsec, and spent a long time kind of finding bugs in that, and I didn't want to run that. And at the same time, I was working on some rootkit exfiltration software. Where I needed a good kind of minimal tunnel to get information out. And I started thinking, well, I can already channel packets through this. Why don't I just kind of make that into something. And the plan at the time was to run my American exit point on my parents' computer back at home to get US internet. And figure like, well, putting a rootkit on my parents' computer, that's probably not a good idea. So I started taking out the nasty code and separating WireGuard, and then it just kind of turned into a thing on its own and seemed viable, and a couple friends wanted to use it, so I made a Git repo where I kept thinking, okay, I finally got it, now it's done, and I would squash down the Git history to a single commit called initial scaffolding.
Oh my God.
So there's like the one initial scaffolding commit for so long. And then even after that, I was fine sharing it with 2-3 friends, but I didn't want to put some crap code out there with bad crypto or anything else. So I really spent a lot of time writing and rewriting, working through every algorithm over and over and over. Just kind of a process of iteration. Every time I would fix one part, 10 more ideas would spring up for other parts. And so the whole thing got written a million times. And then around the same time, Trevor was getting going with his noise project. And very early on, I had sent Trevor an email. I think I had read his thing on 3DH or something. He said, hey, by the way, I got this new noise mailing list. And at the time, noise had really just begun. It was very, very far from what it eventually turned into. And so some of the things I was working on with WireGuard then went back into noise and vice versa, where I wound up actually implementing nearly every revision of noise that we did on the mailing list. Every time there would be a change, we go, all right, well, implementing that. And then I'd play around with the kernel design, see what needed to be changed. And we kind of went in this feedback loop for a long time there.
So were you trying out basically every permutation that the noise framework was coming up with to see if kind of that was the one that you wanted to use for WireGuard, or whether you could just do it in WireGuard as an option?
Not quite every different noise handshake pattern. I mean, there are a lot of them, and they don't all have the same cryptographic properties and state machine properties. But even the handshake language evolved over time. So when I say implement every revision, I mean like every time we made a change to what noise is, I implemented that. As far as the actual handshake, it was pretty clear to me what the kernel requirements for that were early on. It needs to be, one round trip as possible, minimal state. But I had kind of the basic idea of what things needed to look like in the code. And then it was a question of, all right, how can I make the crypto work there?
So you were working within some pretty specific constraints from the beginning. One of them was, you were trying to... It evolved out of a need to exfiltrate data, and you needed a very small payload for the tunnel to run, right? Just the software to make it run, which ruled out like all this IPsec stuff because it's pretty heavy in terms of communication on the wire, but it's also like a bunch of code to actually make the thing go. Is that correct?
Yeah, code needed to be small, but that's also kind of an aspect of just the security of the whole thing is
okay.
I want to be able to keep the whole code base in my head at once. Mm-hmm. And something I apply for, writing code that will be used defensively, but also it's something that matters to me a lot offensively too. If I'm going to be running some spooky code on a weird system that's not mine in a strange environment where it's not supposed to be run, in some corrupt memory context or whatever, I really want to understand every bit of that code.
Yeah.
I could keep in things small and just that I could keep it all in my head at once was a big important part, which kind of goes back to what Thomas was saying about IETF designs versus kind of me just doing it. IPsec is big and complicated, and it does a lot of stuff. And some of the stuff it does very well. It's tons of different use cases. Everyone got their little part of it, and it's extremely useful. But as a result, keeping that all in your head at once is really complicated. And, maybe you can keep a couple general ideas of the RFCs in your mind, but then what about all the implementation details? And maybe eventually you can get a whole implementation in your head, but then how much kind of fades away from what you're able to think about all at once? It's just
it's presumably the case that no rootkit author has ever embedded IPsec into their like a clean room IPsec implementation into their rootkit.
Yeah, I don't think so.
Like this size is one huge comparison between WireGuard and IPsec and OpenVPN. For I guess there have to be people hearing this that aren't really already read into why WireGuard is so great. So if you were going to give me like a couple of more reasons, a couple more distinctions is a better way to put it, between WireGuard and kind of classic IPsec, like what would be your like top 3 there?
Top 3. I don't know about top 3, but I can give you just a couple as they occur to me. So another thing WireGuard focuses on is stealth and kind of a silent state machine, where if you're not sending traffic, it doesn't do anything. And kind of connected to this,
or do anything in memory, or
doesn't do anything on the wire.
Okay,
so,
it's not like keep alives or anything like that.
Yeah, so the keep alives go away if there's not actually traffic to send, and if you send traffic to WireGuard that it doesn't recognize, it just won't respond.
Good.
And so, kind of attached to this then is a very stubborn state machine, where everything moves around with timers, so that attackers can't really influence much from the outside. Even if you send legitimate packets, the most you'll do is crank a timer, but you won't be able to elicit some immediate response or move the whole state ahead by 1 notch. You'll just schedule a timer to happen when it's going to happen anyway. Mm-hmm. So it's very stubborn. You annoy it to do something, and it'll get around to doing it maybe if it feels like it, but it won't ever really respond to you. So these kind of go together as being just kind of like stealthy, small property where it hides on the network. It's resilient. The crypto, as another thing, in WireGuard is also not ancient. It has, one set of ciphers with a provably secure construction, and that's kind of it. It doesn't have a bunch of options for what to do with those. You can't configure your, RSA bit size, though I suppose somewhat post-quantum RSA, with gigabit keys and stuff. But nope, unfortunately not with WireGuard.
Well, I have questions about post-quantum stuff. We'll save that for later.
Sure. And so it's not configurable. The choices in it are good, reasonable choices for, just about every reasonable use case. And if they ever break, it's the same as if the software's got a bug, and then we just change to something different.
I think it surprises people. Like if I look at reactions to WireGuard's design, from people that are somewhat familiar with VPN protocols, I think that's a surprising detail of WireGuard for people. It looks at first, I think, to some people like it's a bug, although it's a huge feature. And I think it's counterintuitive why it's a feature, that WireGuard doesn't have cipher suites, doesn't have configuration, doesn't do negotiation, right? Like it's a single set of, primitives, and then people's reaction to that is generally, well, what happens if one of those primitives break? And I guess we all have thoughts on that, right? But there's a general kind of train of thought right now among cryptography engineers that the path you're taking of selecting just a couple of primitives and sticking with them, and then versioning the whole protocol is the right path to take. And I wonder how clear that is to people that aren't paying attention to cryptography engineering, why that's a win.
Yeah, I think in the beginning of the project, this caught a lot of people off guard. It struck a lot of people as a red flag even. Like, oh my God, no cipher agility. What are we going to do?
Yeah, I remember at NSS, the academic security conference in 2017, you were there because you had published WireGuard at that conference. And I remember sitting out in the lobby or something and hearing a table of people from Cisco talk about, that WireGuard thing looks pretty cool, but clearly no one's going to use it. There's no key distribution and you can't pick your ciphers. It's just not possible to use.
Yeah, but
there's no key
the
distribution
answer to this
in
question
SSH either.
It's true. The answer to this question, what are we going to do when the ciphers break, is the same as, what are you going to do when there's a heap overflow or something? It can be dealt with the same way in this day and age. Maybe the conditions around that were different in the 90s or something. Ciphers were breaking right and left. No one trusted anything. I don't know. But I think certainly now, Chop Poly, Curve to 5 of 19, that stuff is fine.
Yeah.
I think that, like a VPN situation, you have pretty good control of both endpoints.
Yep.
Like you're not usually just letting random people connect to your VPN.
It's not TLS.
It doesn't have to support every
Right.
device on the internet and kind of provide a rolling upgrade path in the same way that TLS does. Like, you can just run 2 versions at once for a little bit if you need to, or just do a hard cutoff.
Yeah, I mean, this connects with something else you just mentioned, which is there's also no key distribution in it, which is another one of these weird things where I see this as a big strength of WireGuard, but a lot of more wary people see that as, but the other things of key distribution, that's clearly missing. It's a problem. But indeed, as you said, for the most part, you have control over both ends of VPN and a VPN context. And by sticking with just basic static keys, the whole configuration gets super simple. The attack surface gets really small. And then people are able to put their own thing on top of it. And so we've, seen a bunch of different solutions and products and projects and all sorts of things come up where people have their own take on how should WireGuard keys be distributed. But importantly, it's not, you always must use X509 and, let's put another ASN1 parser in the kernel, and it's just not necessary.
No, let's not.
Yeah.
And there's a kind of humility to that design, right? Like, I think a stumbling block for a lot of other systems is, like, you look at the set of features that people are potentially going to want, and you feel obligated to implement them all yourself, like to build them into your system. But, like, I think it's probably safe to say not a lot of people have built interesting new networking systems off of OpenVPN, right? Like, people have done a lot with OpenVPN, but, like, there aren't systems built with OpenVPN as like a building block. Like, this is our new protocol, and like the kernel of the protocol is OpenVPN, because OpenVPN has opinions about absolutely everything, and your system is simple and really orthogonal is a cool thing about it, right? Like, it's really easy to build things on top of it because you don't have a key distribution thing built in, right? You just have, a mechanism for keying both sides of a connection, and then it's up to the integrator or to the next level up to kind of, come up with those things.
Right. It's just a building block. And even in the tooling that the WireGuard project provides, for people who are running this on their laptop and just want to have kind of personal situation, there's a little tool called WG Quick that, is what kind of most people use. But actually, that's just like a crappy bash script I wrote, because it just uses the basic things under the hood. And then for people who want more robust things, there's a API to use it, and it can be integrated in that way. But it doesn't prescribe any of that. And the hope is that people will maybe figure out more interesting designs than traditional PKI for distributing keys. And, we've already seen this in the mesh space, seen it a lot in containerization. Also, a lot of systems people have kind of already have an existing channel for distributing keys.
Right.
Some people run WireGuard in, Kubernetes, which already has this massive distribution system for config, and so adding WireGuard keys to an already existing trusted channel is just a no-brainer. Whereas if you're trying to, do that with IPsec or OpenVPN or something, then you're adding this additional weird PKI thing on top of that. And what you wind up doing is trying to recreate basically this notion of pre-shared keys, but into some PKI that doesn't really fit well.
Could you talk a little bit about how what you call crypto key routing works in WireGuard, just because I think that is really cool, and also like the thing that kind of makes all of this building possible?
Sure. So the concept's based on configuration key that's called allowed IPs, which is maybe not named so well. Perhaps it should be tunneled IPs, but it's allowed IPs. And the way this works is on the way out, it's a routing table. And on the way in, it's an ACL. And I mean that like this. When you send an outbound packet, WireGuard will look at the destination address of that packet. and see, okay, which of the peers is configured for that destination address. And if it finds one that matches using the usual prefix matching that routing tables use, then it will encrypt that to the peer's public key, after a handshake and such. On the way in, when it gets a packet from a peer, it will look at the source address of that packet, and it'll say, okay, were I sending a packet to this source address, which peer would I send it to? And if that peer is the same as the peer that actually sent you the packet, then it's considered to be authentic. So it's a kind of an ACL there, or reverse path filter. And the nice property this gives is a mapping between public keys and IP addresses. So from the perspective of a network service running on a system, if it comes from the WireGuard interface and from a given IP, then you can know with certainty that it's an authentic packet and it's really from that peer. So you don't need to have any additional complicated stuff in your firewall about keys or any WireGuard specifics. You can just use IP addresses. In some way, it's like the model of RSH, but the R host model, but it actually works. It's actually cryptographically identified. Now, I'm not advocating we go back to using R host. It's a terrible idea for other reasons, but for just the basic binding between pub key and IP address, this crypto key routing concept winds up being really kind of powerful thing for administrators.
And so WG quick just kind of sets up a 1-to-1 roughly connection, if I remember correctly, and sets the allowed IPs in.
Yeah, WG quick will look at a WireGuard config, which contains private key, listen port, a list of peers. Each peer has a public key, a list of allowed IPs, and optionally an endpoint, maybe persistent keep alive. WG quick adds on a couple things to the basic WireGuard thing, where you can also throw an IP address in the config file, so that it'll set the IP address for the interface, which isn't a WireGuard thing. That's just normal Linux networking, but it's convenient, so it's just thrown in this bash script. It will also add all of the allowed IPs from each of the peers and set those as routes to the interface, which again isn't a WireGuard thing. It's just a Linux networking thing, but it just automates it. So WG quick is just the kind of easy wrapper around Linux admin stuff.
Yeah, but I think the core insight there is that you can manipulate the routing table as just like on Linux. You don't have to push out a config that has everything in advance. You could build a system that's dynamically editing these things in the same way that you're dynamically constructing routes, just like you would on Linux.
Yeah, sure. I mean, the WG quick config files are generally just static, but you could very easily make a whole dynamic system to do this too instead.
So we're talking a lot about Linux networking. I think the most important implementation, or at least up till now, the most important implementation of WireGuard has been the Linux kernel implementation of it. It runs everywhere, right? Is there a mainstream system right now where there isn't a decent WireGuard implementation? I mean, I think all the phones, you have a really good one on Windows now. There's one on Mac OS. You got pretty much coverage right now, right?
Yeah, I mean, I'd say the one in last place right now is the Mac one, because we still don't have a kernel implementation there.
Right.
But everywhere else we've got in the kernel. There's Windows kernel implementation came out recently, super fast, crazy code writing for NT kernel. Can talk about that in a bit if you like. There's one for FreeBSD, for OpenBSD, and then Linux covers Android, and actually it's now in the Android 12 kernel, which is really nice.
Wait, what? It's it's stock Android now?
I think
so it's they haven't built out the user space component of it, so you still have to be rooted if you want to actually use it. So hopefully that'll be in the next version, but it's now in the builds for the kernel. So all the phones that are coming out this year will eventually have user space support that uses the kernel component. And if you've got the WireGuard app and you root your phone, then it'll opportunistically use the kernel implementation.
So I think a thing that's hard to get your head around is that the original WireGuard implementation was Linux kernel, and it's in the mainline kernel now. It's part of the Linux kernel. I think a lot of people are wondering how you pulled that off.
Small, easy to audit.
Yeah, I don't know how I pulled that off. I guess
Maybe he's one of the only people besides Linus that understands how to email a Git patch around. I think that's...
A part of that story that I think is super significant that people don't really talk about or really care about because it's slightly mundane, but super important to the success was that I backported WireGuard to every Linux kernel back to 3.10.
Oh my God.
So I always developed against mainline, but then I maintained this super crappy compat.h file, which like did the worst if-def hacks to like transform the code using the preprocessor to run on old kernels. It's still there and still maintained and as awful as ever. But that worked, and it allowed people to start using WireGuard long before it was in mainline or even a thought in mainline. And so once that was there, then I could go around to each of the distros and say, hey, by the way, I've got a package for your distro that will allow people to add this with just one line. So it worked on all the distros. And then it was available and people started using it.
That's incredible.
And then,
like, that's a non-trivial piece of work.
Yeah, and kind of, boring, bad work too, just like the compat stuff. I mean, it sucked, but I think necessary. And even for my own usage, I wanted to run it on, a crappy old edge router, which runs 310. So, I had to do it. And then once people were using it, and especially once Linux kernel developers themselves were using it, then it was, hey, why are we compiling this out of tree? Can we get this in tree? Then it just became naturally like that. At the same time, I gave a few talks at Linux conferences and, talking to folks on the mailing list. And it's a community I've been part of for a long time and written other parts of the kernel and so forth. So,
what was your other kernel work before that?
I'm actually the author of the SIPhash implementation in Linux, which is fun.
Huh.
There you go.
I don't know. There's some like ARM arithmetic routines I wrote, just a bunch of kind of random things around the tree. I've been on security at kernel.org for a really long time, doing security stuff there. And I've kind of been doing both sides of the Linux kernel security game for ages. So I don't know. It's a community I'm familiar with and know people in.
And like the general path was you're kind of open source out of tree back to 3.10 or whatever, kernel package. And then after that distros. And then after that kind of talking to, about having it in mainline. What was like the first distro? Did you get were there like any distros that were difficult to get this done with? Is there anything interesting there?
No, nothing too interesting. First distro was Gentoo because I'm a Gentoo developer, so I just did it myself. Ubuntu is always a horrible distribution to work with. Just like
why? Before I switched to Mac OS, I was on Ubuntu for a long time.
Well, they sort of inherit from Debian, but they're like not super tuned in to what's going on and like not really on top of things. And so it's just it's still a pain to like make sure Ubuntu is working well. But I don't know. There's not too much interesting to say about the distro story. It's just, open source politics as usual.
What about on Windows? Is that a kernel module or is it actually in the Windows kernel proper?
So it's a kernel driver. So everything in Windows is a kernel driver. Even their networking stack is multiple kernel drivers. There's NDIS for the devices, and there's TCP/IP for the upper layers, and there's NetIO that kind of glues it all together, and NDI proxy to talk to user space and so forth. But, Windows was a really crazy implementation. It started out as a port of the Linux code and then kind of took on a life of its own. And it has super fast crypto in it and really deep integration with Windows. The funny thing about developing for Windows is it's really like an archaeology of computing. There's just trash upon trash upon trash. Everyone in different generations has added their own way of doing things to Windows, and nothing has ever gotten removed for compatibility reasons. And so it's just like sifting through the dumpster and trying to understand these historic relics, which is on one hand really awful, but on the other hand really kind of addictive and interesting. And so I've spent ridiculous amount of hours in IDA Pro now, just taking apart their networking stack and finding weird bugs, but also just figuring out how to make this thing work well and be fast. And that WireGuard for Windows implementation does a lot of strange, undocumented stuff to make it work well, but I'm quite happy with it.
What are the strange
Windows
undocumented
things? Yeah.
Say more.
Boy. Let's see. It works around bugs in an old layer called TDI by just disabling it, moving around it. I don't know, it integrates with the service manager in a weird way where you have services begetting services. It's using a DNS setting API that's undocumented.
That you literally found in IdaPro?
Yeah, I can't program for Windows without IdaPro. Every major function of that thing I'm taking apart in IdaPro. I can't program without the disassembler these days, even for Linux where I have the source where most changes to WireGuard I compile and will then look at what's happened or like after a set of changes. And that's just kind of part of my like compile, run, then disassemble is like the last step. But with Windows, that kind of like obsessive way of coding really gets out of hand because I don't even have source to look at to start with. So if I'm calling some function, I want to understand what it's doing, what the side effects are, what's happening in memory, and I can't just look at the code like I can with Linux. And so it's extremely time consuming. I mean, everything's got to go through IDA. And yeah.
I feel like we need more. I hesitate to call you a cryptographer, but you are a protocol designer. And I mean, you implemented CPASH, so you're practically a cryptographer. We need more people designing and implementing protocols that are literally decompiling things to make sure that the state machine that they have designed is doing what they intended to do when they implement it. Because I don't hear other people talking about how they made sure that the thing that they designed is doing what they think it's supposed to do, like you do right now.
Yeah, I mean, it's not just state machines too, but crypto as well. If I write some curve code, or if I write, cha-cha implementation or something, even the reference implementation in C is gonna make some funky code, and compilers are weird. I want to understand what it's doing, how it works. So
yes.
Even that stuff has got to be taken apart.
Yeah, I think this is more an indictment of like the fact that even C, you don't know what the hell the compiler is going to do. Like we don't have particularly good tooling for writing lowish level stuff that isn't just like writing assembly directly, and we don't have good tooling for doing that either.
Like, and I was gonna, say something like, "Oh, Rust lets you do things, blah blah blah." But even for Rust, people are like extremely excited to have a keyword to inline assembly to get that to stabilization because they need it. And so yeah, even then like the highly typed like compile time guarantees and memory safety guarantees of like your LLVM backed Rust, people still want to inline their assembly to guarantee that it'll do what they think it's supposed to do.
Also, I think in a lot of cases where you'd want to look at that, you'd end up being in an unsafe block anyway, but maybe I'm just a negative person.
Negative Nelly.
Like, the Linux implementation of WireGuard is written in kernel C. It's kernel resident memory unsafe C code. Tell me why I should trust it. Why shouldn't that like revolt me?
I don't know. It's kind of scary. I mean,
oh, come on.
I agree.
I don't know. I just wrote it.
Yeah, I mean, it's worrisome, but I suppose there are mitigating factors. It's very carefully written C, and there's not a lot of it. And so it's something that you can look at and assess and look for bugs in a sitting or two. It's not like it's the task of reading the entire kernel, reading a massive implementation. It's a small implementation. And so, the many eyeballs theory is mostly BS because, if the code is big enough, many eyeballs don't want to do anything, that's it's too much work. But WireGuard hopefully is interesting enough and small enough that it can be done as a casual project. But also just the attention that's gone into the code is considerable and maybe different than a lot of other C projects where things are added and features are added at an alarming pace. It's also been designed to be implementable in a way that's secure or leads itself to be secure. There's kind of a fixed amount of state so that you don't have to have dynamic memory allocation.
Yeah.
All the messages are fixed size, so you don't have any parsers. No parsers, you got no parser bugs. And so kind of a bunch of different coding techniques like this lead to a C implementation that isn't doing anything too scary.
They're parsers, but they're not dynamic. They're not reading like the following message is, n bytes, and then you try to trust it that it's actually n bytes, and you're not going to read a bunch of thing and try to parse it as a type that it lied to you about. It's like everything is a fixed size, and it either fits or it doesn't fit. And if it doesn't fit, you throw it away.
Yeah, that's right. So,
Okay.
So a message. So the parsing action that happens is looking if a message is exactly the size or
Yeah.
if it isn't.
Yeah.
And then after that, it's just dumped into a struct, and that's it.
So this leads me to asking about, so what if all of these asymmetric primitives that we built into this thing are broken by, say, a large fault-tolerant quantum computer sometime in the next 10 to 20 years? How can we make the things bigger so that we can fit some of our favorite post-quantum primitives into these messages?
Rodents of unusual size? I don't believe they exist.
Yeah, so PQ WireGuard is a topic that comes up a bunch. I mean, first I should mention WireGuard as it exists has a kind of a post-quantum safety hatch in it where you can mix in an additional static pre-shared key.
Nice.
So you, in
Love
theory,
it.
could negotiate normal WireGuard tunnel, and then through that tunnel, use something reliable like TCP to run, McLeese, where you've got a lot of stuff to transfer, but doesn't really matter because you got TCP, and it's authenticated already, pre-quantum, but authenticated already for now. And then once you get the result out of McLeese, you pop that in the pre-shared key slot, and now you have post-quantum forward secrecy.
Mm.
So that exists now. That's kind of the current solution. The reason it's done that way is because I think at this point, no one really knows, aside from maybe McLeese and other code-based things, which post-quantum primitives are going to be the ones that make it. NIST competition isn't really over.
It's almost over.
If you looked into this, maybe a year or two ago, you think, well, this lattice stuff has been around for a while, but now people are starting to look at lattices and, hey, are these really the best proposals for them? How are we coming up with the parameters? And maybe it'll all be fine. Maybe it won't. I don't know, but it's clearly very early with post-quantum primitives for putting that kind of thing in the kernel. So it doesn't.
Oh,
do
yeah.
that.
Yeah. In the kernel, yeah. No.
Wait,
But at
is
some
this
point, you're
post-quantum
right.
wrapping up?
That,
It's got another year to go. We're on round 3, and there's three round 3 finalists for key establishment, chem. And there's 3 finalists for signatures. Signatures has gotten less attention because we care more about the long-term key establishment. There's also runners up, and my favorites are in the runners up. So the psych isogeny stuff is in the runners up. But yeah, they're almost done.
So the 3 finalists right now, are they all lattice? No,
think
one
they
of them
are.
will be McLeese, right?
No, I don't think McLeese is a finalist. Let me check. Oh, sorry. There's 4. Yeah. Classic McLeese, Crystal's Kyber, which is lattices, Entru, which is lattices, and Saber, which I think is also lattices. And then for signatures, Crystals, which is lattices, Falcon and lattices, and Rainbow is not lattices. It's codes or polynomials or something.
Jason, you do cryptography work. Do you have opinions on lattice cryptography or elliptic curve isogenies and stuff like that? What's your take on that? Are you enthusiastic about this?
I am enthusiastic, but my feeling now is if you got to design a system, figure out how to use McLeese in it, despite it being expensive. I mean, if you got to design a PQ system, it seems like McLeese is the conservative choice, and the others are really up in the air. But getting back to your original question, so post-quantum WireGuard, what's the deal? So yeah, if in, 10, 20, 30, 50 years, depending on, who you're talking to, who needs the budget or whatever, there's quantum computers, everything breaks. And now we also need post-quantum authentication that's online, etc. Now we got to redesign things. And it seems to me that if things continue as they are with the types of designs that have come out, the WireGuard design in general is going to need some big adjustments. Now, it is, I think, technically possible to kind of shoehorn a bunch of PQ stuff now into WireGuard's design. Like it does static Diffie-Hellman, but there's Seaside, which, can kind of do that.
And you don't want to do static with Seaside, but you can use Psych, which is just a tiny bit larger.
Okay, sure. And, maybe that's fine, but then you also probably want to add some elliptic curve stuff on top of it too. So you have pre-quantum security.
Do a hybrid.
Messages start to blow up, but importantly, computational complexity starts to blow up. And now you're sending little UDP packets, or big UDP packets that have no other authenticating information into the kernel that does a lot of computation on them. And seems like that leads to DOS and all sorts of other ugly things. Or maybe you get rid of the static, but now you've got another round trip. So now the state machine blows up.
If you were talking to somebody who does not know what the hell you're talking about when you say Seaside and static, Deirdre, you want to demystify?
Okay. So SIDH is super singular isogeny Diffie-Hellman. Instead of using elliptic curves to do a Diffie-Hellman key agreement, you do a walk in a graph of isogeny maps between elliptic curve classes. So just say elliptic curves. And you'll start at one curve and you do a walk in the graph to another curve. The secret walk is the isogeny. That's your secret key. And the public curve that you walk to is your public key. And you're able to do something with this walking on this curve graph that's Diffie-Hellman-ish. It's not really Diffie-Hellman because there are no groups. This is not abelian. There's a commutative aspect because of the way the isogeny maps commute. I'm using air quotes. They commute. When this was originally proposed, you could theoretically do a static SIDH key establishment. There is a static adaptive attack against a long-term static SIDH key so that you could make multiple queries against a static key and you would get enough bits from that to break it in, if you have a 700-bit field, you would do like 700 key establishments against it, and then you would have broken their static key. Psych, which is super singular isogeny key establishment, is the submission that was proposed to NIST. And it basically takes Psych and it wraps it up in like the transform that lets you do, it's sort of like turning it into an encryption key establishment. And it turns it from CPA secure to CCA secure and protects against this active adaptive attack. So you can use it for a static key and ephemeral, but you can use it for a long-term static key, which you need in current WireGuard, and anything else such as signal protocol. It's just a little bit bigger. I think it went from 300 bytes to 300 some more bytes for a public
and
key.
This is all kind of important for WireGuard because like a big difference between WireGuard and other kind of public key, secure transports is that WireGuard is based on noise, which is in turn like based on essentially triple Diffie-Hellman, right? So, the common architecture of internet, cryptography protocols prior to noise was you'd do Diffie-Hellman if you wanted forward secrecy, if you wanted every connection to essentially have its own keys, but you'd be doing ephemeral key Diffie-Hellman. You'd be making up keys. In theory, you're making up keys on both sides of that connection for every new connection. The keys just, they get thrown away when they're done. They don't have any meaning. In triple Diffie-Hellman, what you're doing is, and then for those protocols, for those old, the old school, secure transport protocols, to kind of break the man in the middle tie there, you would sign, right? You would do a signed Diffie-Hellman, right? Triple Diffie-Hellman actually just uses nothing but Diffie-Hellman. And there's this, you have ephemeral keys, and then you have long-term kind of static identity keys. And so you need to be able to do a static Diffie-Hellman on both sides to kind of mix in the identity key to that connection.
So WireGuard actually does 4 Diffie-Hellmans in this case. Does static, ephemeral, static, ephemeral. But the original 3DH gets a bunch of properties without static in there, sure.
And then the idea being, once you've done you do all of these Diffie-Hellmans, either the 3 for Signal or the 4 for WireGuard, and you literally like feed them all into your key derivation function. And then you can ratchet. If you're in Signal, you just keep ratcheting your keys forward every time that you send messages back and forth to each other, or not. I don't think WireGuard does that, right?
WireGuard will redo the entire handshake every 2 minutes.
Awesome.
More or less. So it just throws it out and starts over. And then there's another kind of limited state machine where it'll kind of juggle between 3 different states, current session, next session, previous session, and it'll rotate those according to some rules. So you don't have to allocate and such. But anyway, I was going somewhere with the post-quantum thing, which is, one design is you just...
It's our job to keep you from getting there.
You can just kind of go PQ primitive shopping and, find the ones that fit in a 1500 byte or 1280 byte UDP packet, see what you can pack in there, and, you come up with something for the first message. Either you give up on the static thing and introduce a half round trip, a trip, I guess, or you throw it in there and hope it's secure. But and there have been papers to this effect. It's a legitimate academic exercise to go through and find out what primitives and parameters and whatnot will make this work. And you look through the WireGuard paper and you see the security properties it's got, and then you try and match them all up with the thing you're proposing. And it's a successful paper, fine. But I think it's ultimately too expensive and too prone to DOS. And the whole thing with WireGuard is it gets away now being so light because there's just not that much crypto. Curve 25519 is small and cheap and well understood. And so we can be kind of very loose with this one round trip handshake. So I think new designs that incorporate post-quantum crypto are in some ways going to have to give up on one round trip, which is unfortunate, but also there are some security drawbacks of one round trip. With one round trip, you get identity hiding, but you don't get forged secrecy for identity hiding, for example. And so the noise patterns that do more than one round trip wind up needing to store state on both sides.
To figure out where
which
you
doesn't
are.
really fit well with WireGuard. But what I think would be possible for future protocols, maybe future revisions of WireGuard, etc., is to go back to the old cookie idea where the sides aren't storing state; they pass the state back and forth either with like a hash seed or encrypted with some locally cached key they keep around for a certain amount of time. And so you don't need a state machine on both sides with a bunch of memory. You can just kind of rederive things. And then it's a question of how do you organize the protocol so that redriving things from, a little bit of information by the time you're at, message 4 or 3 or something is cheap. And, it's a little complicated, but I think it's also been done before and isn't impossible.
And this is
I think
one of the
that
patterns
kind of
in
design.
TLS, right? Like is it 1.3 where you can encrypt this is 0 RTT? You're encrypting a bunch of this stuff. I forget. Maybe David knows. It's not a cookie, but it's state.
Yeah, so the 0 RTT, has similar issues with forward secrecy on the authenticator. But yeah, you have a little stored piece of information that you send, and the other side can hang on to something to decrypt that and then resume a session.
What would you say to the isogeny stuff has very small keys, so it would fit in the 1 round trip. But the computational complexity of doing the key establishment with that is larger, and putting that in the kernel might be a little bit more than people want to do.
Yeah, so I mean, you could do it, right? And people have made these proposals, and it's probably not too hard to implement if, you can come up with a decent implementation of the actual primitive, which is hard in itself with these things. But still, you got this DOS issue. And I mean, WireGuard already has this DOS issue with 25519, but it works around it with these 2 cookies it adds to the messages, these 2 MACs it adds on.
I see.
Where basically you have to prove that you know who you're sending a packet to. And if the other side is under a load, it'll then ask for another round trip, basically in a stateless way, so that you prove that you control an IP address. Then you can token bucket rate limit that IP address. And so that could also work for doing some isogeny stuff that's a little more expensive, but also in practice it's hard because even if you're rate limiting, you're still processing a lot of those messages, and that still uses some amount of CPU. And with Cryptography, it's a lot, but it's not too much, hopefully, depending on the hardware.
But stuff's a lot more than that.
Yeah, so it gets hard. And it seems like if we're to go back to the drawing board anyway, maybe we want some additional properties that you don't get with 1 round trip. So the next challenge is, how can we add more round trips while keeping the state machine just as small? And there's the other aspect of the timers around that state machine and retransmits and so forth. You don't want to wind up with something crazy like DTLS, but it seems possible, but there's work to be done there. And anyway, I think that's probably what the future will have in store for the post-quantum stuff.
Yeah.
What do you think the future has in store for an RFC or a standard for WireGuard? And what's your take? What do you want the future to be there?
Yeah, I've started writing an RFC a couple times. I've got some drafts of it around. I think I could probably send it up and get the informational one published. And some people would say, wow, now, WireGuard is RFC, 1, 2, 3, 4, 5, 6, and now it's super legitimate or something, even though it's just informational. It gets that number and then people think it's important. But I'm not sure how productive it would actually be in the end, what that would actually give. Another aspect too of WireGuard as a project that gets overlooked is it's not just about the protocol. It's also about how the implementations work. And that's not to say that you're specifying implementation behavior. That's the wrong thing to do. I actually mean it in an even more detailed way, that it's not just implementation behavior, but implementation technique, I think, is important. Where it's not enough just to have, a certain domain range of an algorithm. I actually want the way it's implemented to be really solid, down to how the memory allocation works and so forth. And so as a project, I've tried really hard to have high quality implementations that live up to that. To that extent, I also worry that publishing an RFC might send the wrong message, where, it sends the right, bits on the wire. It's done. That's good enough for WireGuard, but really that's not good enough. Which, a lot of IETF folks will disagree with. A lot of, very legitimate internet people will disagree with. But I think when it comes to making a secure protocol, the implementation stuff is really just as important as how the protocol itself works.
And the design of the protocol being small enough lends itself easier to a better and tighter implementation. But you're right that it's sort of you hand over the specification and you don't know what people will do with it. It might be compatible, but it might not be anywhere near what you and your collaborators have produced in your own code in the official WireGuard repositories. But it's very good because I remember before when it came out, I was on Mac OS, so I used the Golang wrapper or whatever, and now there's the Golang one, there's Rust, there's the Android kernel stuff, there's the FreeBSD stuff, there's the Windows stuff now. Like, you basically have something officially WireGuard compat approved for almost every platform, and they're all very good. And that's amazing because not every project has like the resources and the capability and the energy to actually be like, yep, I've looked at all of these and they are up to snuff, rather than be like, here's the spec, someone go please implement it. Like, I just need an implementation that is compatible. Like, I'm desperate.
Yeah. I mean, I'd say that's a good summary. I mean, there are a lot of protocol documents out there, so I mean, you can read it and learn about the protocol. It's not like, you use this phrase like hand over the protocol, but like, it's out there. There's no secrets or obfuscation or anything like that. It's there. But I don't want to kind of encourage like the way that part of the internet thinks about things. By going the RFC route. I still might do it, but I'm not super, I don't know, I'm not super enthusiastic about it right now anyway.
Sure. Ooh. Support or integration of hardware or enclave-backed keys. That would be neat. Like, you would have your long-term WireGuard key pair backed by like secure enclave on your your Android or your iPhone, or your, secure element on your MacBook or something like that.
Yeah, that'd be cool. On iOS and on macOS, the storage for the private keys are in the keychain, which then use some hardware back stuff. But of course, the computations are happening on the CPU, so you can leak it that way. So putting it down in some hardware would be nice. It's always a little tricky to do with Diffie-Hellman stuff. It's not like a signature where, you don't have to worry about how many things it signs and what it signs for leaking keys. Mm-hmm. With Diffie-Hellman stuff, that's, possibly a little more complicated, where if you're just doing Diffie-Hellman on another device and you give it stuff to multiply, can you trick it, extract the key, all that. So things are a little more complicated there. So I think to that extent, people have looked at doing the whole WireGuard handshake on dedicated chips. I know a few different projects, all currently private and commercial, that are trying to make ASICs and custom hardware to do that kind of thing. And I hope those succeed. It'd be cool to see.
Yeah.
Do people use WireGuard, or do you have an opinion on using WireGuard as just a transport and not a full, like a layer, I guess this would be layer 5 transport rather than like a full layer 3 VPN?
Would you find a way to use WireGuard instead of TLS? Like, do you think do you think there's enough of a win to, there are things people don't like about TLS, although maybe less so with 1.3. Like, if you had to pick between 1.3 and WireGuard.
Well, the comparison there doesn't really fit, because TLS running over TCP, which gives you a reliable stream, and WireGuard doesn't. So then it depends on use case, but maybe between like DTLS and WireGuard would be the better comparison. But
well, you could run quick over it or something.
Yeah, I guess. So what I had hoped would happen was that the noise pipe stuff would take off to replace a lot of TLS use cases, where you could, pick some noise handshake, not necessarily IK, the one that WireGuard uses, but XK. You have additional packet, and you get some other security guarantees out of that. And that would be a neat TLS replacement. It's just a kind of straightforward thing you can run over TCP. But WireGuard itself indeed does work fine for doing, I guess in this case, like layer 4 stuff or layer 5 stuff. I was talking online with someone building a WireGuard pipe the other day. We're looking at ways to kind of work around the crypto key routing stuff. So you really only have to set a couple bytes, and then you don't need a full IP header. So it is possible, and I think works well. But for most use cases where you want reliable stuff, something like noise pipe probably works better. You mentioned quick, which is interesting. What I would expect to happen in the next couple of years with Quick in general in this space is start to see Quick-based VPNs. There are tons of TLS-based VPNs. Quick gives you way more possibilities with those because it's UDP, so you don't have the header line blocking stuff, and you don't have to use DTLS. Quick kind of has it all. But also running Quick inside of WireGuard, that seems superfluous since Quick already has a bunch of crypto bolted onto it. So as far as mixing the worlds, I don't know about that.
All right. What's next for WireGuard?
Oh boy, I don't know.
What's coming up?
Let's see. Hopefully we'll be getting the free BSD implementation actually merged into their kernel. It's still out of tree.
Nice.
So yeah, and there's a little bit of work on their crypto API going on there. I hope in the next year to finally put some attention onto the WireGuard Rust implementation.
Cool.
We've had one sit in the repos for a while, but needs to be reviewed, cleaned up a bit, and then I think we'll be able to send the announcement email, hey, this is ready, build things out of it. In the last months, I've been putting tons of energy into the Windows stuff, and that I expect to continue for a few months still to kind of get that fully ironed out and done. That software is trying to be like a real system component of Windows, so it seems like it came with the OS is what it's striving to do.
So great.
And that winds up being way more time consuming than any of the other platforms for the reasons we discussed. So that'll be going on for a bit.
As an Android user, I look forward to the kernel level WireGuard to be exposed from. I've been using the WireGuard on Android user space app for a long time. So I love that. But if it's kernel level exposed, that'll be even nicer.
Yeah, so that's another thing. Hopefully, will be coming up is working with the Google folks to write their user space for that, but also for Chromebooks. I think we're going to be adding WireGuard there too, and so there's some interesting tooling and plumbing that's going to hook that up and expose that in the UI. So hopefully there will be some things about that coming out in the next few months.
Are you aware of Fuchsia OS?
Yeah, I mean, I know about Fuchsia.
Not a podcast episode unless Deirdre mentions Fuchsia.
Hey.
Okay.
Hey, I've already mentioned the isogenies. We've got WireGuard in Rust. We should just throw it at the Fuchsia folks and just make it part of their. Well, they have a microkernel that's not in Rust, but everything else is in Rust. But
that would be a cool idea. I remember talking to them a long time ago about using something WireGuard-alike for, what were they talking about? Like their Bluetooth stack, or I don't know, some kind of crazy IPC, something crazy that didn't seem to fit, but it was on their radar. So
I'm glad.
Yeah, okay. I think that could be something neat.
I know a little birdie or two, and I could just be like, hey, you should just put this in your tree.
Just add it. Just do
it. It's ready to go.
Once
practically.
The Rust implementation's in a good spot, we'll print it off and then physically mail it to Fuchsia people.
That's what I did with the WireGuard paper originally.
You printed it out?
Physically mailed it. So I wrote that paper, and I didn't really have anything to do with academia at all. I'm like, I didn't, where do I send it? Who's going to look at it? Who will break it? So I printed out a copy and I physically mailed it to DJB.
Nice.
He didn't respond to it, but I figured like if there's any chance like of,
it's like I built a protocol
what to do with this.
Using almost all of your crypto primitives. Like tell me where it is broken, if anything. Yeah. Did he ever hear back?
No, and then, years later, finally met him at a conference. He was like, oh, yeah, he sent me that in the mail. It's on my desk somewhere. Oops.
Amongst all the papers.
I think, and not recently, but, maybe a couple of years ago, some of the flack that WireGuard got was from people that were really big into formal verification. And, there's a notion that, any new, major protocol, major secure transport we do should be designed with formal methods. And should be directly provable in some model that we already have. How compelling do you find that argument? I know you've done some stuff with formal analysis for WireGuard.
I mean, I think it's a compelling argument. It was used in context to say NDSS never should have accepted the WireGuard paper because it didn't come with a formal security proof. And
whatever.
That seems unreasonable because for, the most concrete reason at NDSS, I met this guy, Kevin Milner, who was working with Cass Kramers at Oxford.
Mm-hmm.
He was like, hey, that looks cool. Have you ever heard of formal verification? Have you ever used Tamarin?
Yeah.
I said, I have never used Tamarin. And then we sat down at the conference and he showed me to use Tamarin. And then a few months later, I was hanging out with him up at Oxford and, banging out the first proofs of WireGuard.
There you go.
Had it not gone NDSS in the first place, that never would have happened.
Yep.
And since then, formal verification now has just become part of my general flow of doing these protocols. I think it's an important tool without a doubt. And I guess that variety of stuff, automated solvers, also has been useful for me for just hacking things. I wind up using SAT solvers for doing little implementation proofs for crypto things. Like if I'm writing some funky C code to like change the base of some limbs, oftentimes I'll want to prove that and I'll break out the SAT solver. But it's equally as useful for hacking stuff. I want to see how some weird code works or find unusual paths through it. I can load the assembly up in something like Anger and run bool vector from the SMT output of that. And so I think in general, these techniques, symbolic model for crypto, computation model for crypto, SAT solving, etc., have just become part of a tool set that's super useful across the board.
Love it. I want to learn more about that, but I work on a cryptocurrency, so I have enough things to work on.
Well, hey, if anything needs proofs,
Yeah, we have a network protocol, and we've got a bunch of protocols all smushed together. You have to figure out which one you would like to formally verify. But where's the low hanging fruit?
I think Bitcoin fixes this.
What?
When I was doing the state machine for WireGuard, I indeed didn't know about Tamarin. That didn't happen until I met Kevin. But I sat down on my floor and taped a bunch of pieces of printer paper together, and then just started drawing it. And
drawing WireGuard, the protocol, and the flow.
drawing the state machine. Working it out. Got it. And the goal was to, convince myself that the state machine was sound. And it's
do you still have that paper?
Rigorous, but nah, unfortunately not. It'd be fun to have, but
you could have auctioned it off.
Oh God. Oh man.
I mean, that's not far off from if you were trying to encode the state machine as literal state transitions in types. So for a bunch of stuff in Rust, it's literally you cannot represent one of these states unless you consume the memory of one of them, of one state, and transform it into another. That is the only way in this implementation that you're able to do this. So literally writing it down on paper is the first step to doing that. And then the next step is to write it as transitions between types and then compiling it and making sure that the flow actually works as you think it does. So,
sure. Yeah. I mean, underlying that process, of course, is a bunch of type calculus for why that theory is sound, why it works out using types.
Yeah.
All right. Aside from paying for and winning an auction of your state machine pieces of paper, how else could people support the development of WireGuard?
So the project lives on donations. I'm living off of donations. If you go to wireguard.com/donations, there's a forum. You can send money. GitHub sponsors there's a link there. There's a Patreon. If you run a company, you want to give a lot of money, we can throw the logo on wireguard.com/donations. But that's how the project ticks. I mean, it's tried really hard to kind of make it an independent project that's not financed by some product that would bias it, and isn't in the pocket of some huge company. Just kind of this independent thing with a mailing list and so forth. But that also means that the funding is random, just comes from anyone pitching in and from a lot of great companies that aren't trying to be the project, but appreciate the project and want to see it live on doing its thing. And so that's been real helpful.
I just went to check if I was already sponsoring WireGuard on GitHub, and I am. So full disclosure, I'm sponsoring one of WireGuard's many GitHub sponsors.
Oh, thanks. This is nice of you.
Awesome. Jason, thank you very much for joining us. This has been wonderful. I'm learning so much from you, and you're not worthy. We're not worthy.
Thanks for having me on the show.
I would have talked more and annoyed Jason more, but there's a rock saw going in my backyard right behind us.
This is cool. I need to go learn Tamarin.
Me too.
Just take a second real quick. Sell us Tamarin. Like, you make it sound very cool and very easy to pick up, and I've never even considered it. So, sell me a Tamarin.
It sounds like a mountain to climb.
Tamarin's cool. So Tamarin is like ProVerif, but better, way better. So if you use ProVerif, it's like the same thing. If you haven't, the deal is this. They've got a domain-specific language where you write each message and who it's transmitted to and how it's computed. And if you use a hash function, you have just a generic thing called a hash function. You're not specifying that it's Blake or Shaw or something. So you can kind of write down the flow of the protocol generically, which means it's a symbolic proof and not a computational one, because you're not looking at what are the exact limits on the number of messages and that kind of thing.
Okay.
Once you've written down a description, then you can write down what you want it to prove. That if you send these messages and then these messages, this next message won't be readable except by this other principle. And it has a little bit of temporal logic built in as well, so you can order things based on a time 1 and a time 2. And so it's a kind of very expressive language. You can write down the whole flow of the protocol and then all these different things that you want to prove. And then you tell it to prove it, and it will use tons of RAM and CPU, and it probably won't succeed. It might, which is cool when it happens, but it probably won't. And at that point in, say, ProVerif, you can you can choose different things. You can give it some more CPU and memory and have it run longer and hope that it will work then. Or you can write some helper lemmas where you say, actually, you look at this hash chain this way, it reduces to this, so just assume that it's clear, and then maybe that'll help out the prover. Or with Tamarin, the really cool thing that makes it great is it has a web interface where you can then click through the different paths that a proof can take.
Yes.
And it'll show with graph viz output of okay, here are the assumptions we can make, and then move on to the next step. And so you can kind of click through these and see visually where it's going in the proof. And so
you can catch it should not be able to go in this direction, but the way that I have written it down says that it can go in this direction. You're like, that's bad.
Yeah, so you can say, go in this one instead and visit that area. So you can say, all right, go here and now try and prove it again automatically.
Yeah. And
so usually you run it, gets to where it is, you click a few times, and then it'll finish it off. And then you can encode what you've just clicked into helper lemmas and such. Kevin wound up fixing a lot of the internal logic of Tamarin. It's a big Haskell program, so that it would better choose things for WireGuard's proof, which is nice. This interactive aspect is very cool. The interactive aspect makes the whole thing fast enough that I can use it as a real tool in development, because it's not like I write up the protocol and then I got to wait 3 days for it to finish or something. Yeah. I can write it up, click through it a little bit and see if the thing I just wrote up is stupid or if it works. And you think, when you're doing crypto, you just shouldn't be stupid, period. But actually, when you've got a prover, you can just write down whatever occurs to you and see if it's solid. Kind of a guess and check, which is a very nice way to develop things.
So once you write this down in this DSL, and the thing that you wrote down in your DSL is good to go, you have to go implement that in the real thing that you want to deploy. And how do you check for divergence? Just by eye or what?
Yeah, so with something like Tamarin or Pro Vera, yeah, it's really two different implementations because you're writing in this domain-specific language, and so if you're mapping one to another, yeah, it's just that it's the same. You just hope that it's the same implementation.
Okay.
Which it's better than nothing, but you would like it to be the same. There are other projects like Hackle Star out of INRIA, for example, where they're able to write implementations of protocols in a language called F star, and then prove things about that implementation, but then also lower it down to C.
Yeah. And they're doing this for TLS or something, or pieces of TLS.
Yeah, for pieces. And they've even done this in other parts of the general project with primitives.
Nice.
So not just with protocols, but like with, is this actually Cha-Cha? Or is this actually Curve 519? And what's cool with that is, like I was saying, with protocols where I can, mess with it a little bit and, do silly things to see if it proves, they can make optimizations to their curve code that are speculative, not super well thought out, but will probably make it faster, and then see if it's actually correct after.
Like
instead of having
in the protocol in Tamarin's view of correctness.
Well, so I'm talking about for Hackle Star. So like if they're working on a curve implementation, like of Curve 519, let's say, and they see, oh, actually, if we just omit these steps or rearrange these steps or do this a little differently, the code is going to generate this faster. Then they can just check immediately, is it also correct? Which is really powerful because most of the time when you're writing super optimized code for primitives, you spend a lot of time like carefully scrutinizing your math to see, is this optimization legit? And then, I think the math checks out. Hopefully it's okay.
Yeah. Or like I'm windowing just this much for this field to try and get a speed up, and it should be correct and all my test vectors are passing, but like, maybe it did something weird at an edge case or something. Yeah. Yeah. And, when it's just you in front of your computer, how much are you hand waving for yourself and how much are you actually being rigorous? It's a hard thing to do. So I think these tools are really important where you just can develop fast and then it checks you. Yeah. Cool. So I guess to bring back that back to WireGuard, it would be cool to have something like a Hackle Star WireGuard implementation. We looked at various times at doing that, and I think the code it generates still isn't super suitable for the kernel, but maybe it'll get there in time. But the other aspect is that WireGuard's trying to be simple enough that you can just look at both things and see that they line up. Yeah. That hopefully the manual version is sufficient. Yeah. Hopefully. As opposed to TLS, or IPsec, where it's just like, it's so complicated that you kind of can't eyeball it anymore. And so you're just like, yes, if we have a computer checked proof of the thing that we're spitting out, we're more confident in that. Whereas if the thing is small enough to be WireGuard, you can just like look at it and just be like, yeah, it's small enough that a human or two can just hold it in their head and grok it, as opposed to like the complexity of IPsec or TLS, even 1.3. Awesome. Okay. Thank you, Jason.
Thank you for doing this.
Yeah, yes. Thank you.
Sure.
This is great. I learned stuff. And we may keep bugging you about, although like literally you enumerated all of the paths forward, so there's nothing to say for several years.
I don't know. If you think of something cool or like if you want to actually pursue a certain path, I mean, I'm happy to.
I may fork the Rust WireGuard and just be like, here, this is how you slot in a nice Rust implementation of Psych, and this is what it does. And you could just say, this is too much or too little or too complex or too DOS-y or
whatever. Or go back to your cupboard under the stairs, Deirdre. What a nice implementation. You get a cookie. Okay, now go home.
It's like, it's very nice. You can go use it. You yourself and only you.
It's just the opinions I have on like, should we do PQ now or later and how should it be done? I mean, they're opinions, but they're not like super strong.
Oh,
and
yeah.
you might find that in the practice of implementing it, you come up with something pretty cool and good and worth doing anyway. So it seems like good research to do either way.
Oh, yeah. It's definitely research because it's basically there are no obvious options. There's trade-offs in every axis. So it's all sort of like, okay, let's try some stuff and find out where we get burnt, because we're going to get burnt somewhere. We either have to change the protocol we're trying to retrofit. We either have to compromise on some of the security levels of some of these primitives. We have to, we either have to accept that these things are going to be slow. Like there's trade-offs everywhere. So we got to figure it out. I don't know, because we have to figure something out before we ask people to try to adopt it.
If you're just trying to slide stuff in, you could probably do Psych and Kyber,
It'll just be
do
slow.
a hybrid of them.
Yeah. That's basically the direction I would go. And we'll figure out signatures later. We can do Max. We don't have to worry about signatures. Signatures are like TLS and other stuff. Anyway, I'll stop talking.
We can get Chris Pikert on later this month under the guise of it being a discussion about post-quantum crypto, but actually he and I will spend the entire time talking about the upcoming Michigan versus Ohio State football game.
I was going to say that it should be under the guise of Michigan football, and then I will grill him.
We're swapping around. There we go.
About post-quantum primitives. Awesome.
Okay.
Thank you,
Jason, thank you for doing this.
Yeah,
yes.
thank you.
Sure.
This is great.
My
I
pleasure.
learned stuff. Anyway. Cool.